we're going to look at nth roots. We're also, just take a look at the title there. We're looking at nth roots and real exponents. And I'm going to say the word rational a lot. We're really looking at rational exponents more than anything else today. Rational exponents are exponents that are fraction. Rational is anything that can be expressed as a fraction, and so we're really looking at fractional exponents a lot today. Nth roots. Let's go ahead and start talking about nth roots. Nth roots. A root uses a radical symbol. Radical is different than rational. A radical symbol looks like this. Typically, we see it as a square root, where we have an understood index of 2. But nth root means, hey, look, we're talking about all of these, not just square roots. This could be a 3. Of course, this could be a 4. It could be a 5, a 6, a 7. It could be all kinds of different things. So we're just talking about nth root. All right. So let's get into it. First, let's take a look at what we have right here. We have the 4th root of 81. So we're talking about specifically a 4 as the index. And if we're talking about a 4th root, we're looking for a group of 4 of the same things. So we can take 81, we can simplify 81 so that it is composed of 3's. 3 times 3 is 9, times 3 is 27, times 3 is 81. And look what we have right here. We have 4 of the same thing, and so we can take 4 of the same thing, we can bring it out to the front as 1. So there is 1 3 left over with nothing left on the inside of that radical, so the answer is simply 3. Notice they have it right there. That is the answer. Right here we have a negative 4th root of 81, so a negative 4th root of 81 is 3, so our answer is a negative 3. Down here we have both positive and negative 4th root of 81, and so when we take the 4th root of 81 and get 3, we have positive and negative out in front, and so that's our answer. Now this brings me to a very important thing that probably throughout the course you're going to have to deal with, and so you do need to know when this is true. Now, when the book, when a test, when a problem already has a root in it, it tells you, based on what's in front of that root, if you're looking for a positive and negative, both positive and negative answer. So if it's already provided, you use based on the context of the problem, okay? But if you remember, even in the previous lesson when we talked about completing the square, we had to put both positive and negative in our answer, even though it wasn't provided for us. So the difference is if you choose to use an even root to solve something like an equation, where like in that completing the square problem, we took the square root of both sides. That was an even root. If you choose to use an even root to take the square or to solve an equation, then you must provide both positive and negative. We have to account for all of the possibilities because we're trying to find all the solutions to that equation. So we have to account for everything. If it's provided for us, we do what they want. If it's understood to be positive, we call that the principal root, and that's a lot of times what we see. Okay. Now, let's continue to look at this fourth root of 81 for just a second. We said 81 was 4 threes. Well, we can also write 4 threes as 3 to the 4th power. We know this simplifies down to be 3. We know that's the answer. We've already solved it. We already see the answer over there. But let me use this to help introduce those rational exponents I told you we were looking at today. Well, rational exponents are changing this so that it's in the form of 3 raised to the 4 over 4. To change something from radical form to rational form, the index is always in the denominator of our fraction. Notice the base stayed the same. The index is in the denominator, the exponent's in the numerator. So when we change this to a rational exponent, 4 divided by 4 is 1, and this leaves us with 3. And that's kind of nice. Let's change the problem just slightly. If this was the 4th root of 3 to the 6th power, no, let's go 3 to the 5th power. Let's just make it 3 to the 5th. Okay, well, we could write this out 1, 2, 3, 4, 5 threes. We could look for a group of 4. We could bring it out to the front, and we can see that there is 1 3 out in front, and there's 1 3 left on the inside. Bring it out to the front. It's still a 4th root of 3 left on the inside. You could write that out. Sure, you could do that. But that's more work than what you really have to do. We could see this as 3 raised to the 5 over 4. What is 5 divided by 4? 5 divided by 4 is 1 with a remainder of 1. When we take 5 and divide it by 4, we have 1 with a remainder of 1. 1 3 on the outside, 1 3 came out, but 1 remained on the inside. That's the technique that I'm going to want to use to simplify these things. Whew. First one, a negative square root of 49. Well, we know the square root of 49 is 7. There's a negative out in front. Bingo, bango. We took care of it. Right here, we have a cube root of a fraction. Well, first, we can break that cube root up to both the numerator and the denominator. The cube root of 64 is 4. The cube root of 27 is 3. Finally, the 4th root of a negative 121. Well, 121, we just start trying to deal with this. 121 is 11 times 11. And we see pretty quickly that there's not two things. 11's prime. Even if we split this up to be the 4th root of negative 1 times the 4th root 11 squared, there's not 4 of these. And we don't know anything that multiplies times itself 4 times to get negative 1. So all in all, there's no way we can simplify this. So this is as simple as we can get right here at the beginning. That's where we're going to leave it. Okay, some simple properties right here. We kind of just used that last one on the last slide. We can go both directions with this. We can split this up to be 2 different fractions using the same nth root on the top and bottom. Also, if we're multiplying the same root, notice that's the same index, together we can multiply the stuff on the inside, okay? All right, so take a look at this first one. Yes, we could work that one all the way out, or we can use what we know. This is the same thing as n raised to the 18 divided by 6. 18 divides by 6 evenly. This is n cubed. This is n to the third power. There is no remainders. There are no remainders, right? 18 divided by 6 is 3 with a remainder of 0, so nothing is left on the inside. That is as simple as the answer gets right there. That's it. We simplified it. We didn't have to write out 18 n's. I don't want to do that. Let's take a look at this one right here. First, you may get terrified when you see a plus 1 to the 12th power, but you shouldn't. Okay, actually, let me go back to this previous problem because I just realized something we do want to be aware of. When we are taking radicals, if we take an even root of an even exponent of a variable, well, we need to make sure this answer is positive, right? If we're taking an even exponent, even root, this is a principal root, we need to make sure this is all positive. We need to make sure it works out all right. So we have to put absolute value signs around this. N cubed is not guaranteed to be positive. It's not. So we need to put absolute value signs. And the rule here is even, odd. An even index of an even exponent giving us an odd outcome, we need to make sure we put absolute value signs around that. That's not the end of the, this isn't the most important thing. The absolute value, it's not the greatest, most important thing that we're going to talk about in this course, but that will come up. You'll see that on the answers in the book and things. More than anything, I care that you can simplify it down to get n cubed. But going the extra mile, putting the absolute value signs when you need to, the rule is even, odd. Okay, that's when you do it. So let's take a look at this right here. Let's look at this one. Notice right here we are doing an even root of an even exponent. So we're gonna have to be careful, right? We're gonna have to be careful. So like I was saying, a plus 1 raised to the 12th power does look a little terrifying. It looks like there's a lot going on. It looks like maybe more than what you want to deal with. But it's not that big of a deal. A plus 1 raised to the 12th power, this is the same thing as like x raised to the 12th power. It's just something raised to the 12th power. So instead of writing a plus 1 to the 12th power, I'm just going to write x to the 12th power, okay? Is that all right? I think it's all right. Let's break this down to be the 4th root of 81 times the 4th root of x to the 12th power. It's the same thing. The 4th root of 81, we did that a lot earlier, it's 3. X to the 12th power, 12 divided by 4, remember our rule, our little, like we did over here, 12 divided by 4 gives us 3. Because of that even, odd rule, we do have to put absolute value signs around that to make sure it's positive. So this is 3 times the absolute value of x cubed. Although it's not really x, it's really a plus 1. So if you changed that earlier to make it look easier for yourself, change it back at the end because we want to represent the real simplification of the real problem. Right here we have the square root of 63y cubed. So I'm going to simplify this. I'm going to break this down. So we have two separate things to look at. The square root of 63. 63 is 9 times 7. And I know the square root of 9 It's 3. So I dealt with the square root of 63. Now, y cubed, a square root is understood to be an exponent of 2, so this is y to the 3 over 2. The index is always in the denominator. Y to the 3 over 2. 3 divided by 2 is 1 with a remainder of 1. So there is 1y on the outside and 1y left on the inside of that square root. We simplify this by multiplying the outside stuff together, keeping that square root, and multiplying the inside stuff together. We're done. There's no even, odd, because that is an odd exponent to begin with. It was even, odd. So we don't have to worry about absolute value signs. It's not that big of a deal. Finally, take a look at this fifth root. Well, first I am going to split this up like I did on the previous promise. The fifth root of -1 times the fifth root of p to the 10th times the fifth root of q to the 7th. Separating it all out. The fifth root of -1, what times itself? 5 times gives us -1, -1. Fifth root of p to the 10th, 10 divided by 5 gives us 2 with a remainder of 0. 2 p's are on the outside, no p's are left on the inside. 7 divided by 5 is 1 with a remainder of 2. Notice right there, there was some q's left over, so they're still inside the radical, and the index stays the same. The index doesn't change. Just like right here, it was a square root at the beginning, it's a square root at the end. Here, it's a square root at the beginning, or it's a fifth root at the beginning, it's a fifth root at the end. All right. We've been talking about rational exponents. Here they come. All right, we're going to see them a little bit more. One thing they want you to notice right here is if there's no exponent on the inside, it is understood to be 1. So this would be 1 over again, whatever that root is. It's the same rules we've been talking about. All right, we're going to simplify these using, if we can use rational exponents to help us out, we will. Right here, a lot going on. I notice we have different numbers. We have 32 on the top, 2 on the bottom. But 32 is part of the progression of 2's. 2 raised to the 5th power is 32. That is a 6th root of 2 on the bottom, so I'm just rewriting that so it looks a little bit easier to digest, lots of 2's. Now I'm going to change this to my rational exponents. This is 2 raised to the 5 over 10 divided by 2 raised to the 1 over 6. Because that was that 2 was an understood 1. Change that exponent. This does simplify down a little bit. 5 over 10 is 1/2. Notice we have the same base on the top as we do on the bottom. Recall your exponent rules. Our exponent rules say if we have the same base, we can subtract the exponents. This is 2 raised to the 1/2 minus 1/6. 2 is the base, but we're going to subtract those exponents. This is 2 raised to the 3 over 6 minus 1 over 6. We have to get a common denominator to subtract, which leaves us with 2 raised to the 2 over 6, which simplifies down to 1 over 3. Just take it one step at a time. It's a lot easier than it looks. Right here, 4th root, x to the 21st with y to the 15th. Well, I'm going to split this up like we've been doing. And I'm going to simplify each of those. 21 divided by 4 is 5 with a remainder of 1. Right? Yeah, I was thinking about this as that 21 over 4. We've been doing that a lot. 21 divided by 4, it's 5 with a remainder of 1. That 1 is on the inside of the fourth root. 15 divided by 4. 15 divided by 4 is 3, right, with a remainder of 3. Again, same thing. 15 divided by 4, how many whole, how many are remaining? We simplify this by bringing it all together. That stuff on the outside, x to the 5th, y cubed. And then we have the stuff on the inside, xy cubed. Finally, right here, we have 16 to the 3/4 over 16 to the 1/4. Well, the first thing I can do is I can just say, hey, this is the same thing as 16 raised to the 3/4 minus 1/4, because it's the same base. Subtract the exponents. This would be 16 raised to the 2/4. 2/4 is 16 to the 1/2. Anything raised to the 1/2 power is a square root, and the square root of 16 is 4. That's it. All right. You want to approach each of these realizing there's multiple ways to approach it. You don't have to do them all the same way, but all the different ways is the same answer.